Hello, fellow pedestrians. Today we're going to examine something called the exact differential equations. Up until now, we wrote our first order differential equations in their typical solved form of y is equal to function of x and y, right? Which was silently assuming a solution in the form of y is a function of x, with x being its only independent variable. But what if we generalize this and make an assumption? Let's say we have a function, call it phi, which depends of both x and y. And x and y are now going to be the new independent variables. Well, nothing would practically change at all. And the solution would be of the form of the newly founded function, which depends on both x and y, is equal to c, which is just a curve for x and y. Now, the differential equation that has this guy as a solution is a total differential of phi, meaning that taking the total differential of 1 would get the partial derivative of phi with respect to x dx plus the partial derivative of phi with respect to y dy is equal to 0. Now this is going to be an important case. This is an exact differential. And it will prove to be very, very useful for us helping to solve many differential equations because if you already see that this going to be written, it can be written as y prime is a partial derivative combination of a new function which we call phi. Now, if we generalize this guy here, let us generalize. This can be written as a function p of x and y dx plus q, another function of x and y dy, is 0. Now, if this is a partial derivative of a function with respect to one variable, and this is a function, is a partial derivative of the same function with respect to y, the second independent variable, then this is going to be called again an exact differential. Now, from calculus, we do know that for a function that has two variables, two independent variables, it is true that the second derivative, the mixed derivative of both x and y, are equal to each other. Right? It doesn't. The order doesn't care of which differentiation is first to the other. So what we get is that if we differentiate this with respect to y, so this is p, and we're going to denote it as p of y. If this is equal, differentiate the differentiation of q with respect to x, and we denote this as qx. If these two are equal, it follows then that this, let's call it 2, is an exact differential, meaning that p is to be theta phi of theta x, and q is going to be theta phi of theta y, which is very easily solvable because these are both separable differential equations, the first kind of equation we stumble across, and we know how easy it is to solve them, right? Now, this is a case where both the first derivative of this and this, with different variables to be differentiated, when these are equal. What happens if they are not equal? Let's say if y is not equal to qx. Then we need to multiply to this equation here, if it's possible, with something that turns it into an exact differential. Again, if it's possible, it's not always possible. Now imagine that we call this something new, and new will be a function of x and y to start with. This is called the integration function, the integration factor, sorry. And it is only needed when this condition is not true. So when these two are different, we're going to need something called integration factor. Now, how are we going to calculate what this is? Imagine a quantity like this, which will get multiplied. This will still be 0, so you have mu here and mu here. And now the new p and q are going to fall under this condition. So this is what the integration factor is going to do. So to actually calculate it, what we are going to do is multiply the second equation, this guy here, with mu. So you get mu p dx plus mu q dy is equal to 0. And this guy here is the new mu, the new p, sorry, going to call it p tilde, and this is q tilde, right? And now if we take the derivative with respect to y of this guy and equate it, the derivative with respect to x of q tilde, one will get y p plus mu py is equal to mxq plus me qx. And finally, y minus qx is going to be equal to 1 over mu qmx minus p mu y, right? Now, what we are dealing here is a very complicated differential equation. It is a partial differential equation with respect to x and y both. So this didn't really make our lives that much easier. And now the thing is that we can make assumptions, and let's say that mu is only dependent on x. Let's call this 3. Then 3 is going to transform py minus 2x. So this is going to be 0. So over q is equal to me x over mu. Likewise, for mu only depending on y, then py minus 2x. Now this is going to be 0 because there is no derivative with respect to x, over p to be minus y over mu. And if one of these doesn't work, we can try the other one. If neither works, then you cannot find an integration factor that is going to render this generalized function into an exact differential form, right? And this is all the theory there is for differential, for exact differentials. Now, let us move on to examples and see why this is very useful. Let us check an example that can be written and can be solved differently. Let's say we have y dy plus x plus 3y squared, sorry, this is an x, dy is equal to 0. Where if you rearrange all of that, you can check that y is going to be minus y over x plus 3y squared. And if you further rearrange this, you will see that this can be written as a first order linear differential equation, but with respect to x. So it's going to be x of y plus something is equal to a function of y. And if you solve for the function x, then you will find the same solution as we will using the exact differential solution. So using what we learned, this is P and this is Q, right? So the first step is to find Py and Qx. So Py is this guy with respect to y, it's 1, and Qx, this guy with respect to x, which is also 1. And those two are equal. So this differential equation is indeed an exact differential equation. And as we said, we know that P is the first partial derivative of a general function called phi with respect to x, meaning that phi of x and y is going to be the integral of P, which is y, dx. And this is written as xy plus, and pay attention here, plus a constant. But what kind of constant? The most general constant, which is going to depend on y. Why is that? Because if you really differentiate this with respect to x, you will get this. This is a constant because y is treated like a constant here. The same thing applied would apply if you would treat q, you would get a constant that would depend on x, because for q, x is treated as a constant. Now that we have phi, we also know we will take this and differentiate it with respect to y. So theta phi of theta y is going to be, this is x plus derivative with respect to y. But we know that this is q. Q is this guy, x plus 3y squared. So this and this goes away, and this is equal to 3y squared. Or is simply y cubed, right? And finally, to write our solution, we'll know that will be of this form. Our newly founded function that will be equal to a constant, and we know that phi is this, so xy plus the constant we found, x cubed, is equal to a constant. And now this is the solution of this exact differential. Now, of course, we're always going to get an implicit form of our count in our solutions, because this is what we began our assumption with. It was like an educated guess that would work, and it does indeed work. Now, let's go ahead with, like I mentioned, this could also be solved by using the general linear formula for the first degree differential equation, one could easily see that this can be written as dx over dy is equal to minus x over y minus 3y, and this would be your Rx or your Ry in this particular case, and this would be your Py, like we said in the general linear differential equation course. Now, let us check another example where any known and familiar solutions and tricks would not work. Let's say we have something of like x plus e to the y dx, and you could already see that this is a very foreign term to us, having the original function being on e. So plus x e to the y dy is equal to 0. Now, py is e to the y is equal with q to the x. It's easily seen. So what this means is that p is going to be theta phi of theta x. So p is this guy. So x plus e to the y going to be theta phi of theta x, or integrate everything. So x squared over 2 for this guy plus x e to the y, and don't forget the constant which depends on y, because again this is a partial derivative and y is treated as a constant, and we need the most general way to express our constant. And again, this guy is going to be equal to the first derivative, the partial derivative of y with respect to y, so x e to the y is going to be theta phi theta y, meaning that x e to the y plus y is going to be x e to the y. So this is 0, and its integral is just a constant. So finally, this is written as x squared from here over 2 plus x e to the y plus a constant is equal a constant, different constants, so you get a probably non-zero constant, and this is, again, is the implicit form of the solution involving both x and y. You could solve for y, but it doesn't really matter. And it is true that this is nowhere near ND's, this guy I'm talking about, that we stumbled across. It cannot be solved with our familiar methods, and exact differentials seems to thrive in such cases. Now, let's check one last example of importance. Let's say you have x plus y squared dx plus xy dy is equal to 0. This again could be written as y prime is equal to yada yada yada. Doesn't really matter, and I haven't checked if this can be solved with previously gained knowledge. So let's find py, which is 2y, and 2x, which is y. Now these two are different, and we do need to use the notion of the integration factor that we talked about. Like we said, py minus qx over q is going to be mx over mu x over mu. So this minus this is 2y minus y, so y over q, which is xy, is mx over mu x again. So this and this goes away. And what you get is again a separable differential equation, which is of the form d mu dx is mu over x, or d mu over mu is integral of dx over x, and of course mu is just x. Now you can easily check this is the new p, which is the integration factor times the old p. So it's going to be x squared plus x y squared, and q tilde is going to be x squared y. You could check that py tilde is indeed qx tilde, and hence this is a truly exact differential, right? So now we know that p, the new p, is equal to theta phi theta x. So our function curve is the integral, sorry, of p tilde dx, so which is x squared plus x y squared dx. And again, don't forget the constant which depends on y. So this is x cubed over 3 plus x squared over 2y squared plus our constant. And finally, go ahead and differentiate this with respect to y, and we'll get x squared y plus z prime y is going to be equal to what? To q, but our new q. So x squared of y. This and this goes away. This is 0, meaning that this is just a constant. It does not depend on y. And finally, equals a constant, which is this guy here, plus x squared over 2 y squared plus a constant, same thing as before, and this is our final solution in the case where these two guys are different with each other and we make use of the integration factor. Now this pretty much sums all of the theory and examples for the integration and use of exact differentials and how useful they can be when other techniques are going to fail. Go ahead and try if you could solve this one, but I dare you to try and solve, where is it? This one. I mean, go ahead and write this as at this form, which is going to be y prime is going to be a minus, which is it, x plus e to the y over x e to the y, right? And it's not very easy to solve, especially with what we know thus far. So this is pretty much it. Thank you all for watching, and I will see you soon in the next video, where we will try and tackle the second order differential equations. Thank you all.